So to summarize, in case of pure bending, first we have developed a variation of the strain, and we have seen that the strain is varying in a linear way with y. And epsilon x is given as minus y over rho, where rho represents the radius of curvature produced by the bending action. Now, if we apply this formula for the maximum strain will take place at the largest distance from the neutral axis, which will correspond to C, and then we can calculate the maximum strain as C over rho. So we can say that 1 over rho is equal to epsilon m over C. So if we know the value of the maximum strain, we can calculate the radius of curvature. And we know that the strain is related to stress. So also the stress will vary in a linear way. So we can write that since sigma x is E times modulus of elasticity times the strain, then sigma x will vary in a linear way with y. And because epsilon x can be replaced by minus y epsilon m over c, and E epsilon m is equal to sigma m. So we can also express the variation of the stress function of y with respect to the maximum stress within the section. Now, for the stress also, we have another expression developed because we have seen from the definition of pure bending that the bending moment will result from the integration of minus y sigma x dA. And by replacing sigma x by its function, we have seen that we can write the bending moment function of the maximum stress as sigma m times I over c. From here also we define the elastic section modulus, which is m over which is s. So we can write sigma m then as mc over I, which is m over s. So until now we have seen several expressions, if you want, for the value of sigma maximum. We can express sigma maximum as m over s. We can also find, if you want, sigma maximum function of epsilon maximum, because sigma maximum is equal to epsilon m times E. Okay, and if we use this combination, we can replace sigma m in the equation of the stress variation with y in this equation here. So this will allow us to find sigma x function of the y and the bending moment. So in general, depending on the given, you decide which relation to use. Sometimes you know the maximum stress, so you can deduce the distribution of stress within your cross section. Sometimes they give you the bending moment, and this equation will allow you to find the stress distribution function of the bending moment. All you have to do then is to replace here sigma m by m over s, which is the result you got from the previous calculation. And you get then that sigma x is minus y over c times m over s. And by replacing s by its value, which is I over c, then you will get that you have minus y m times c over I. C will cancel out, and you will get then sigma x function of the bending moment, y and I. Now, as we said also, so for the radius of curvature, we can express it as 1 over rho equal epsilon m over c. And if we have, let's say, in a problem, we know the maximum stress, then we can find rho function of sigma m by just saying that epsilon m can be replaced by sigma m over E, which is the modulus of elasticity. So one way to express rho is to say that 1 over rho is equal to sigma m over CE. And since also we have derived an expression for sigma m function of the bending moment, If we want to express the radius of curvature, function of the bending moment, we can replace sigma m by the developed equation we have revised now. So we multiply by mc over I. And as you can see, then c will cancel out. And the radius of curvature can be computed if you know the bending moment applied on your section. So you can say that 1 over rho is equal to, by just replacing sigma m by this value here, you get that 1 over rho is m over ei. This means that if I know the bending moment in the section, and I know the geometry of the section, and the modulus of elasticity, I can directly determine the curvature. If I know also the maximum stress, modulus of elasticity, and the maximum distance from the center, from the neutral axis, also I can get rho. So always it depends on the input to know which equation to apply. You should be familiar with all of these equations, and then you can manipulate them depending on your inputs. We'll practice together in a while problems about how to deal with these equations. Now, if we consider an element subjected to pure bending, we have already seen together that under the effect of pure bending, we'll have the formation of a curvature, okay? And then what will happen is that if we have, let's say here, a moment along positive z, we'll have compression of the upper part, tension of the lower part. This will lead to a reduction of length of the part above the neutral axis and increase of length for the part below the neutral axis. And for this bend, the radius of curvature is rho and is determined by the relation 1 over rho equals to the bending moment over EI. Now, what about if you want the other section, the transverse cross section? This is called here, this is the transverse cross section. Okay. Also, in this section, you will have formation of a curvature. Why? Because you have already established in previous chapters that you can relate strain in different directions. Okay. So if you have here strain in x, epsilon x, and we developed the expression of epsilon x, you have also epsilon y and epsilon z, and they can be related through the Poisson ratio. Okay, so we know from previous analysis that strain along y can be related to strain along x by minus the Poisson ratio times epsilon x. The same for z direction, epsilon z is minus Poisson ratio times epsilon x. And since we already developed for epsilon x the equation, we can replace epsilon x by minus y over rho. Okay, and the minus sign will indicate the following: whenever you have reduction in length in x, you will have increase in length in y. The same along z, and you can see this in the figure. So here, as we said, this part will be reduced in length, so epsilon x of it will be negative. On the other hand, if you take now epsilon z here, you will see that along z I will have increase in length. And for this part here, since epsilon x is positive because I have tension of this part, for z direction, for the transverse section, I will have reduction in length. And this means that what will happen here is that the center of curvature for this part will be on the upper level. However, the center of curvature for the transverse section will be on the lower level. And I can relate the radius of curvature in the of bending, okay, to the radius of curvature in the transverse section. All I have to do is to just look at my expression. Okay, I have that epsilon z is equal to Poisson ratio times y over rho. Okay, already when y is positive, I have positive value of epsilon z because this is expected, because above the neutral axis, I will have increase in length, and below it, I have reduction in length. And we know that the form of epsilon can be written as y over radius of curvature rho prime, which rho prime is the radius of curvature in the transverse section. So as you can see here, and as we said, rho prime is, we measure it from the neutral axis, okay? So this is the neutral axis, the distance from, if you want, the center of the curvature of the transverse section to the neutral axis is rho prime, okay? So this distance is rho prime. And rho prime can be related to rho by just comparing these two relations. So we have that mu y over rho in the transverse section is equal to y over rho prime, which is the radius of curvature in the transverse section. So we can say then that by comparison, that rho prime is rho over the Poisson ratio. Okay, so we can say then that rho prime is equal to rho over mu, or also we can say 1 over rho prime is mu over rho. Okay, so this equation will relate for you the value of the radius of curvature in the transverse section to the radius of curvature in the section of the band. And we say then this curvature is called anticlastic curvature. Now we'll start to do examples on the part covered already. So we'll start first with the following example. So I will zoom a little bit. Okay. In this problem, knowing that the couple shown acts in a vertical plane determines the stress at point A and point B. So here we have two views of our beam. We have first, if you want, the profile view showing us the loading to which is subjected this beam. And as you can see, it's only subjected to a couple. So if I do any section within my beam and I do the statics analysis, I will see that the normal force is 0 because there is no load acting on the beam along x direction. So n is 0. Also, no axial load on my beam. So the shear V is also equal to 0. So I only have the bending moment, which should oppose the action of the couple applied. And my bending moment M should be equal to 15 kilonewton meter. So I am in the case of pure bending. So I can apply all relations we developed together. What they want me to find is to find the stress sigma at point A and at point B. Okay, so as I told you, you use the formula depending on what you know. Here, you don't know sigma maximum, you know the bending moment. Okay, so because we know the bending moment, then you can use the relation between sigma and m we developed together, which is sigma equal to minus my over r. So this is the relation of interest to apply. To get the stress, since we know the bending moment, we should locate the point with respect to what? Keep in mind that y is measured from the neutral axis. Okay, in this equation, y is measured from the neutral axis, and we have established in the course material that the neutral axis should pass by, it should pass by the centroid of the cross section. So the first step here, in order to be able to solve for my stresses at different points, I should determine where is the position of my centroid to find the neutral axis location. Then also I should determine the inertia of my section about this axis. And then I can replace into these equations to get the stress at any point I want. Okay, so the strategy will be first to look at my section, determine the position of the neutral axis, find the inertia about the neutral axis, and then apply the formula. So let us look at the cross section. They gave us the cross section. In this cross section, you have a hole. So it's a rectangular cross section with a hole in a rectangular form. So from statics, you remember that whenever I have a hole, to get the inertia, I should do inertia of the big part minus inertia of the small part. Okay. Now, first, let us determine the centroid location. Okay. Because of symmetry here, the centroid is at the center of the two rectangles. So I can say that the centroid is just here at the middle. This is my centroid C. And my neutral axis should pass by C. And always, okay, here my neutral axis is along the direction that is perpendicular to my bending moment, okay, and perpendicular to the line of action of the bending moment. So as you can see, the bending moment will act along this direction. It will cause compression of the upper part. It will cause tension of the lower part, okay? And this vector moment is along Z. So if you do the right hand rule, you will see that your thumb will point towards the screen. So if I consider this is my Z axis, so let us put them in another color. This is my, if I consider any section here, okay, my bending moment is like this. Okay, in this section of interest, I have that this is the axis, this is y axis, okay, and x is perpendicular, is within the cross section. We cannot see it here in this figure. We can see it in the figure of the profile view of the cross section. So you have, this is x, this is y, and Z is perpendicular to the rectangular cross section. Okay, so here you have that X is, if you want, within the your section. When you do the cut, you can see it here directly. This is X, this is Y, and this is Z. So now what we can say is that the neutral axis will be along X direction, okay? And I will have variation of stress function of Y. And if I want to find the neutral axis position, we said that it should pass by the centroid. So already the neutral axis is the x-axis passing by C. Okay. Now, once I determined the location of my neutral axis, okay, then I can say the following. I can say that for my neutral axis, I want to get the inertia about it. So inertia about x-axis, we call it Ixx, okay? And it is by definition equal to the following. Since we have two rectangles, one full rectangle, okay, and a hole, so we'll say that we'll decompose the surface into two parts. The big rectangle, we'll call it rectangle 1. So in green, it's surface 1. And the small rectangle is surface 2. So this is my surface 2. Okay, and we have that the total inertia is Ixx, or I is I1 minus I2. Keep in mind that the inertias are always calculated relative to the neutral axis. Okay, so as we said, our neutral axis is the x-axis passing by the centroid. So we need to go to formula sheets for a rectangle. We already know that for a rectangle, if you want to get the inertia about this axis, we define the dimension parallel to this axis as b. So let us say for our rectangle 1, we'll put the dimensions in green. This is b1 and this is h1. So b1 and h1. Then we can write that I1 will be equal to b1 times h1 cube over 12. Now you can keep the dimensions if you want in millimeter, and then your inertia will be in millimeter to the power 4. Okay, so if you keep the dimensions as they are, you get I in millimeter 4. You have that b1 is equal to 20 plus 40 plus 20, which is 80 millimeters. You have h1 is 20 plus 80 plus 20, which is 120. So you just have to replace to get the value of I1. Now for I2, you have to take, this is B2. B2 is just equal to 40. And H2 is like this, okay? H2 is equal to 80. So 80 is H2. So now I just have to replace these dimensions to get I2, which is B2 times H2 cube over 12. Okay, and now all we have to do is to just replace and get the numerical values. So until now we got I, we know the value of I. Now what we have the value of M, which is 15, so we can replace into the formula. We start with A. Okay, for A we said that sigma A is equal to minus M times Y over I. Okay, now concerning Y, it's Y of A, it's the distance from the neutral axis. So this is our neutral axis. You have, this is Y of A. Y of A is positive because Y axis is upward. So we have the Y of A is equal to 80 over 2, which is 40. We just have to replace Y of A. Here pay attention, okay? Here you should pay attention for units. You cannot mix units. Already your moment is in kilonewton meter. So if we use the moment in kilonewton meter, okay, then we should convert Y and I to meter. So Y to meter and I to meter 4. Or if you wish to keep I in millimeter 4, then you will use YA in millimeter and you will use the moment in kilonewton millimeter. Okay, so then you should do the appropriate conversion. You know that 1 meter is 10 to the power 3 millimeter. Okay, so you can then replace M by 15 times 10 to the power 3, and you keep YA in millimeter and I in millimeter 4, and at the end your result will be sigma A will be in kilonewton per millimeter square. Okay. And if you want to convert to see the correspondence in Pascal, you have that millimeter square is 10 minus 6 meters square. And kilonewton is 10 to the power 3 Newton. So if you use y and I in millimeter unit and m in kilonewton millimeter, then you will get your stress in equal to, the value will be times 10 to the power 9 Pascal or gigapascal. Okay. And if you convert I to meter 4 and YA to meter, then you will get your result just in kilonewton per meter square, which is equivalent to kilopascal. So just pay attention for units. Okay, you can use whatever you want. Just pay attention for the conversion factors to know what will be your the unit of your final result. Okay. Now, A here will be subjected to compression. Okay, because it's above the neutral axis and the moment is positive along Z. So it's compressing the upper part here, if you consider the section here. So it's compressing the upper part and doing the tension of the lower part, and it's along positive Z, the bending moment. And then I expect to get a negative value for sigma A, since A is in compression. Now, the same procedure for B, same formula, just what will be different is Y of B. B is below the neutral axis. It's characterized by a negative Y. So just I have to say Y of B is equal, from the neutral axis to B, I have a distance of 40 plus 20 equals to 60. So this is 60. And since I am below the neutral axis, Y of B is minus 60 millimeter. So now if I replace in my equation, sigma of B will be positive because B is subjected to tensile stresses. Okay, so this is how I can determine the stress state at points A and B. We can see here the details of the solution. We started by getting the total inertia about the neutral axis. We divided the section into two parts, 1 and 2. And the inertia is I1 minus I2. As you can see here, they converted to meter 4. Okay. Now, all you have to do to go from millimeter 4 to meter 4 is to just say that 1 millimeter is 10 minus 3 meter. And if I have to the power 4, then I should multiply by 10 to the power minus 12 to go to meter 4. Okay, and since here you have 10 to the power 6 millimeter 4, whenever you multiply by 10 minus 12, you get the same value, but 10 times 10 to the power minus 6 meters to the power 4. Now, after getting I, as we said, we just have to apply the relation. Okay, and we don't forget to have a conversion of units. So Y is expressed in meters. Okay, and as expected, sigma A will be negative because you have it's subjected to compression, and sigma B is positive because it's subjected to tension. And as you can see here, when you replace the moment value, even the moment values I converted to Newton instead of kilonewton meters, I converted to Newton meter. And in this way, if you have M in Newton meter and YA in meter and I in meter to the power 4, your final result will be in Newton per meter square, which is Pascal. Okay, so here the value you get is in Pascal, and then since you have it times 10 to the power 6, your numerical value, you can replace minus 61.6 times 10 to the power 6 Pascal by minus 61.6 megapascal, because 10 to the power 6 Pascal is equal to 1 megapascal. Let us do another problem. In the following problem, two vertical forces are applied to a beam of the cross-section shown. Determine the maximum tensile and compressive stresses in portion BC of the beam. Okay, so in this problem here, we want to find what is the maximum tensile and compressive stresses acting in BC. And this example is a little bit similar to what we have introduced in the course material, because you will see that in BC is subjected to pure bending. Okay, and we can see this because if I do a section, I will only obtain a bending moment without, if you want, without any normal or shear force. Okay, now how we can make sure of this? We have first, we deal with external reactions. So the first step will be to find external reactions at A and D. At A, you have a pin. This means that you will have a Y and a X. At point D, you have just dy. Okay, now if you do the equilibrium relations, if you do sum of x equals to 0, then you will get that ax is 0. Now, to get ay dy, if you paid attention for symmetry of your problem, you can just say due to symmetry, ay is equal to dy is equal to 20 over 2, which is 10. And if you didn't pay for the symmetry factor, you just have to write two equations, sum of y equals 0 and sum of moment about any point in your beam equals 0. You get two equations, two unknowns, you find ay and dy. So we can say here that the developed reactions are vertical upward, and each of these reactions is in magnitude equal to 10 kilonewton. Okay. Now, we can say that whenever we consider a cross section between B and C, we have that these two forces will result in a couple. Okay, the couple they create will be a clockwise couple, and the couple created by the other two is a counterclockwise couple, and both couples have same magnitude, which is 10 kilonewton times 150 millimeter, which is equivalent to 1 kilonewton is 10 to the power 3 newton, and 1 millimeter is 10 minus 3 meter. So this is 1,500 Newton meter. Okay, and then I can say that in this case I know what is the magnitude of my bending moment, and portion BC will be subjected to bending action, because I can consider that if this is BC, I have the following action on it. I have from both sides a couple applied equal to 1,500 Newton meter. And therefore, if I do any cut here, okay, I will obtain that the bending moment developed. So if I do a cut here and I reject the other part, the bending moment in this section developed should oppose this one and should be equal to 1,500 Newton meter. So now I determined M, okay? And M is a positive moment along this direction, which is perpendicular here if you want to the screen, and it's compressing the upper part, and it's leading to the tension of the lower point. Okay. Now, in order to determine the maximum tensile and compressive stresses, I need first to locate the neutral axis, because we know that the maximum stresses takes place at the farthest distance from the neutral axis. Here the section is a little bit challenging. This is the section, my cross section. It's a U-shaped cross section. So to find the neutral axis, it will be a little bit more difficult than the previous problem, because I need to locate the centroid of this section first. Okay. And also in statics, you have learned how to determine the centroid of a certain part. Here you have several possibilities if you want in order to determine the centroid location. You can divide your parts, and the first way is to consider that this is a rectangle, rectangle 1. This is rectangle 2. This is rectangle 3. So I divided my part into 3 parts, my area into 3 areas, 1, 2, and 3. And I can use the formula. I am interested just to know what is the height of the neutral axis. Okay, so let's say this is my neutral axis. I want to know the direction of my neutral axis. What is y of my neutral axis? Okay, and I know that y of my neutral axis is equal to y of the centroid, y bar of the section. Okay, so here the first step will be to find a y bar. Where is my y bar? Okay, to do so, I will use a table. If you remember from statics, what is the method to find the centroid location? I need to use a formula. The formula is total area times y bar, or centroid coordinate, equals to sum of ai y. Okay, so now let us do a table to facilitate the calculation. We do a table. We just enumerate the areas 1, 2, 3. We have all dimensions here, so we can easily calculate the areas and the position of centroid for each area. Let us do them together. So if you go back to the figure, for part 1, the area is 10 times 60 in millimeter square. The same, this area is equal because they are due to symmetry effect. You have here, this part is characterized by a length of 50 minus 20, so it's 30 millimeter times 10. Okay, so then we still have to determine for each area the location of the centroid. For the first rectangle, it's at the center of the rectangle, and since the whole height here is 60, so y bar 1 is equal to 30. The same for y bar 3, while for the rectangle here, the centroid is at 10 over 2, so y2 is equal to 5 millimeters. Okay, and now I can use my table to summarize my results. I get the area of each part, I locate the centroid of each part, and then I compute for each area what is a times y bar, and then I use the formula of centroid, that y bar of my centroid is equal to summation of a summation for I going from 1 to n. N is the number of areas I divided my total surface with. AI sigma I bar over total area over sum of AI. Sum of AI is the total area of my surface, A total. So as you can see here, in this table, when you sum the elements of this column, you get the total area. when you sum the elements of this column, you got sum of AI, YI bar. And then all you have to do is to divide this result by this number in order to locate the centroid of your section. And of course, as you can see here, you have that Y bar is counted from the bottom surface because we considered the origin of Y here in the analysis to get the centroid. Okay, so we can say that the neutral axis is at 25 millimeter from the bottom. Okay, and this is then my neutral axis location. Now, you could have divided your surface, of course, in different ways. One possibility, if you want, is to say that I can take the big rectangle minus the smallest one. Also, it's possible. In another way, instead of dealing with 3 areas, you will only deal with 2, but you have to do then, pay attention whenever you have a hole, then you count the area you put minus. So you just have then 2 areas. So first you put a plus with it, the second you put a minus with it, and you do a table to get the location of your centroid. You will get exactly the same result. Okay. Now, once we locate the neutral axis, the second step will be to find now the inertia of the surface about the neutral axis. Here, we should remember what we call the parallel axis theorem. What is the parallel axis theorem? Let's say for surface 1, I know its inertia about an axis passing by its centroid, but I don't know its inertia about an axis which is the neutral axis of interest here. So here I have 2 axes. I have the neutral axis that is of known location, that is 25 millimeters above the bottom line. So this distance is 25. And I know that my centroid here is at a distance from the bottom of 30 millimeter, which is the location of the centroid of the rectangle. Okay, so I can just say that the distance between the centroid of area 1, the axis passing by the centroid of area 1, and the neutral axis is 30 minus 25 is equal to 5 millimeter. Okay, and if I know the distance between these 2 axes, okay, and I want to find the inertia about the neutral axis, I apply what we call the parallel axis theorem. The parallel axis theorem states that the inertia about any axis that is parallel to the axis passing by the centroid. So let us call, if you want, so inertia about the neutral axis here will be equal to the inertia about the axis passing by the centroid of part 1, okay, plus the area of part 1 times the distance d squared, where d is the distance between the neutral axis and the axis parallel to it passing by the centroid. Okay, so now concerning the inertia about the centroid axis, it's from the formula sheet. For a rectangle, we know that it's equal to b1 h1 cube over 12. You have all dimensions. B1 here is 10 millimeters. This is 10. The height is 60. This is why you have here 1 over 12 times 10 times 60 cube. Okay, plus in order to find the inertia about the neutral axis, we should apply the parallel axis theorem. So we should add the area of part 1, which is 600, times the distance between the neutral axis and the axis passing by the centroid of part 1, which was determined to be 5. So now By applying this relation, we got our inertia. Since all dimensions used are in millimeter, then you get your inertia in millimeter to the power 4. And inertia of port 2 and inertia of port 1 are equal to 195 millimeter to the power 4. Okay. So now, in the next step, let us find for other surfaces, area 2 and 3, the inertia values. And for 3, you can directly say, because of symmetry, 1 and 3, here they called them 1 and 2, and 3 is this area. 1 and 2 represent the same inertia about the neutral axis. So no need to repeat the calculation for 2 because you have exactly same dimensions and same distance between the neutral axis and the axis passing by the centroid. Because also here you have the axis passing by the centroid is at 30 millimeter from the bottom, and the neutral axis is at 25. So this distance is 5. So exactly same numbers. So you'll get I1 equals to I2 without need to do any further calculation. Now for I3, for the part 3, which is here, I call this part 3. Okay, what we have to do then is to determine first what is the distance between the neutral axis and the centroid and the axis passing by the centroid of the section. We have seen that because the thickness here, the height of rectangle 3 is 10 millimeter, then its centroid is at from the bottom at a distance of 5 millimeters. And since the neutral axis is at 25 millimeters from the bottom, then the distance now between these two axes is the difference between 25 and 5. So this distance is 20 millimeters. So when you apply the parallel axis theorem, the distance you will use is 20. So here in this figure, you'll have 1/12 times. First, to get the inertia of part 3 about the axis passing by its centroid, this one. Okay, your area is characterized by a dimension parallel to the axis equal to 30 millimeter, and the height is 10. So it's 1/12, 30 times 10 cube, plus the area of the sport is 30 times 10, which is 300, times d square, which is the distance between these two axes. So you can get the value of I3. And now, once we have calculated I1, I2, and I3, we can find the total inertia of the section about the neutral axis. So the total area of the section about the neutral axis is equal to I1 plus I2 plus I3. Okay. Now, once we are done with I, our purpose is to get the maximum stresses. Okay. The maximum stresses can be computed as follows. So we know that the farthest points from the neutral axis will be submitted to the largest values of stresses. So for the upper part, we said that it's in compression. So the top will be subjected to compression, and the farthest point is at 35 millimeter from the axis because the whole height is 60 millimeters. And we already know that the neutral axis is at 25 from bottom. So we can say that y top, which is counted from the neutral axis, is equal to 35 millimeters, while y bottom is minus 25 millimeters. And once we determine the values of y top and y bottom, we'll be ready to calculate the stresses, maximum stress in compression and the maximum stress in tension. So just we have to replace into the formula. Okay, the formula is sigma. So first, sigma top, okay, is equal to minus m times y over I. I is already calculated here. Y top is 35 millimeters. We convert it to meter. M, we already discussed the value of M. M is 1,500 Newton meter. So we just have to replace, we get a negative result because it's in compression. And the maximum tension is found by doing the calculation at the bottom. Okay, so minus my bottom over I. So you have y bottom negative, so minus minus will give you plus, and then you have that, you have the, this is the maximum tension, and this is the maximum compression. Okay. Now, sometimes if you want, if you put sigma compression, you don't need to put the negative sign. So when you put the subscript compression, you can just put the absolute value because you already stated that it's a compression stress, okay? And so sigma maximum compression is 102.4 megapascal, and sigma maximum tension is 73.2 megapascal, okay? Now, which one is more critical depends on the maximum allowable values. Okay, so in general, whenever they give you a problem, they tell you a design problem, they tell you that the maximum allowable tension is equal to this value, and the maximum allowable compression is equal to this value. So you should compare your maximum values with the allowable stresses to determine which more is more critical. Okay, and of course, we should not exceed the allowable values. Let us do another problem. So we have here the following section. Knowing that for the extruded beam shown, the allowable stress is 120 megapascal in tension and 150 megapascal in compression. So this is a design problem. They gave us the allowable values in tension and in compression, and they are asking us to determine what is the largest couple that we can apply. So always we should find what is a maximum to not exceed tension. What is a maximum to not exceed the compression allowable stress? And of course, we select the lowest between the two, okay? Because let's say you will get M1 max and M2 max. To be on the safe side, you should select the lowest between the two, okay? Now, in this problem, we have also pure bending. But as you can see, they reversed the bending moment direction. This means that if you look at this figure, the top of your beam will be in tension and the bottom will be in compression. So what will change if they just change the direction of bending moment? What will change is which part is compressed and which part is in tension. And then the bending will be in the reverse direction. And the radius of center of curvature will be below the beam. That's the only difference, okay? Now, let us look at what we know, okay? So here we need to get the value of M. What is M? In order to avoid, here when we design on the critical condition, we find the value of M, which will give us the maximum allowable tension, and the value of M, which will give us the maximum allowable compression, okay? To start with, as usual, we need to know the properties of the section. We need to find the centroid location. We need to find the total inertia about neutral axis in order to be able to apply our formulas, okay? Now, to start with, we can divide the section in several ways. We can divide it into three areas like this. One rectangle and two triangles, or another alternative to just have two areas is to take the following configuration. You take a parallelogram. So this is a parallelogram, and this is a triangle. This is another option. So here you do just have to deal with two surfaces. This is what they did in this problem. So you know that for part one, the centroid is here. So this is the centroid C of part one. And for the triangle, this is C2. Now, we know that C1 is the intersection of diagonals. And of course, the height of C1 will be equal to 54 over 2. So this is 27 millimeters. Now for a triangle, we know that the centroid is at 2/3 of the height from the extreme point and at 1/3 from the base. So this distance here is 2/3 times 54. So we found the location of centroid of part one, centroid of part two. Concerning the areas, they are very simple. For the parallelogram, it's the height, which is 54 times the base, which is 40. And for the triangle, it's the height, which is 54 times the base, which is 40 over 2. Okay, so now we have found for each surface what is the area, what is the position of the centroid. Then in a table, we can summarize the results and multiply for each area A by Y bar of its centroid. And then we compute sum of A's and sum of AI, YI bar. And then we can find what is the centroid location for my section. Keep in mind, we don't care about X bar. So no need to find X bar. You just need to know the height of your centroid in order to know the location of your neutral axis. So no, don't find X bar. This is the neutral axis. We have found that the neutral axis is at 30 millimeter from the bottom. This is 30 millimeters. Now, we already computed the distance from the bottom of the centroid. So for centroid 1, it's at 27 millimeter from the centroid. This means that D1, which is the distance between the axis passing by the centroid of section 1, parallel to the neutral axis, and the neutral axis, this distance is 30 minus 27. So it's 3. So here also in the table, you can summarize the values of D to facilitate your calculation after. Now concerning area 2, the centroid of area 2 is at 36 millimeter from the bottom. So this is equal to 36. And then the distance from neutral axis is equal to 6. So just here, let us fix this. This is 6. Okay. And now, once we have this table, this will facilitate on us the calculation of inertias about the neutral axis. Okay. So to start with surface 1, which is the parallelogram. For the parallelogram, we can find the formula of the inertia also in a formula sheet. It's similar to the formula of a rectangle. It's equal to this distance, which is parallel to the neutral axis, D1, times the height the height separating your opposite sides. So this is H1. So H1 is equal to 54 and B1 is equal to 40. So this will give you the inertia of the parallelogram about an axis passing by its centroid. Now, since you are interested into getting the inertia about the neutral axis, you will apply the parallel axis theorem. So you should add plus the area of the parallelogram, which is 2160, times the distance D between the two axes, which is 3 square. And then, because all your dimensions are in millimeter, you will get your inertia in millimeter to the power 4. Now, for the triangle, also same procedure, but you should use the formula that is for a triangle. For a triangle, for about the inertia about an axis passing by its centroid is, instead of 1/12, it's 1/36. B2 times H2 cube. This is cube. Okay, so this is a triangle. This is the axis passing by its centroid. Then B2 is the distance parallel to the neutral axis. And H here is the height relative to the base. So H2. In this problem, we have that B2 is equal to 40 and H2 is equal to 54. So we do 1 over 36, 40 times 54 cubed to get the inertia about the axis passing by the centroid. And then to transfer to the inertia about the neutral axis, we add the area of the rectangle, which is half B2 times H2, times the distance between the two axes square, which is 6 square. And then we'll get I2 into millimeter 4. And then all we have to do to get the total inertia is to add I1 plus I2. Okay. Now, once we have this information, okay, we can also find y top and y bottom because we located the neutral axis. So let us find y top and y bottom in order to find the corresponding relation between sigma maximum and the bending moment. So you have that neutral axis, your neutral axis is at 30 millimeter from the bottom. So this is 30. So you can say that y bottom, so y bottom here is minus 30, and y top and y top is 54 minus 30, minus 30 is 24 millimeters, because the whole length is 54. Now, please keep in mind here, because the bending moment is reversed, so m is negative. So in general, the formula was sigma equal to m minus m times y over I. Here, because m is in this direction, that it's compressing the upper part and doing tension for the lower, the upper part is in tension and the lower one is in compression. For this case, the convention of bending moment is that it's a negative moment. So here, keep in mind when you replace here is to replace m with a negative value. Okay, so m here will be negative because it's compressing the bottom and doing tension to top. But what we care here is about is the absolute value of m, the magnitude of m. Okay. So in this formula, when you replace y top by 24 millimeter and m by a negative result, you will get at the top a positive sigma, because as expected, at the top you have tension and at the bottom you have compression. Okay. Now, since we care about just the magnitude, we can talk about absolute values. Okay, so we can say that the absolute value of m maximum 1, okay, is equal to absolute value of sigma top, which is in tension. Okay, so the top is in tension times times I over y of top. Okay, this will give us the first value of magnitude of moment to not exceed the maximum allowable tension. For compression, since compression takes place at the bottom level, so the second value, the absolute value of M2 is the absolute value of Y compression, the sigma compression that is imposed, the maximum allowable compression, times Y I over Y bottom. Okay, so just you should pay attention here that the top is in tension and the bottom is in compression. So when you use the allowable the maximum allowable stress for compression, you use with it y of bottom. And when you use a sigma tension, you use with it y top. Okay. While if your moment was reversed, if you have in the problem moment like this, then with sigma compression, you use y top, and with sigma tension, you use y bottom. Okay. And now what we have to do is to compare the two values and select the smallest one, because you don't have to exceed any of these two. Okay. So as we said, the top is subjected to tension, the bottom is subjected to compression, and we can accordingly find what is the maximum moment to not exceed the maximum tension, and what is the maximum moment to not exceed the maximum compression. Here they are equal. It's a particular case, but in general, if they are different, you will select the smallest between the two, because you have to satisfy both conditions. So the moment maximum should be below this value and should be below the second value. Okay, so to satisfy both conditions, I will take the maximum moment as the smallest between the two. Here, since they are equal, this is a specific case, a particular case due to the geometry of our figure. But in general, they might be different. And then you select the smallest value of the maximum moment. Okay. Let us continue with problems. In the following problem, we have a 60 Newton meter couple is applied to the steel bar shown. Assuming that the couple is applied about the z-axis as shown, determine the maximum stress and the radius of curvature of the bar. Solve part A, assuming that the couple is applied about y-axis. So as you can see here, the bending moment vector can be along, it's a vector along the cross section. It can be along y, it can be along z. Okay, in both cases, you will create bending. Okay, because the condition for bending is that the vector bending moment will be within the section of your, within your cross section. Okay, because if you put a vector like this, then your moment will be along z direction. And if you have, if you put a couple like this, then it will be along y direction, but both will create bending effects. Okay. Now, in the first part, in part A, we are considering that the couple is along z direction. And the neutral axis is always along the direction of the moment vector. So in the first scenario, you have that the moment vector is along z. This means that your neutral axis will be along z and parallel to z. And then you have that the stress variation will be along y. So stress will vary with y. In the other scenario, when you put the vector moment along y, then the neutral axis will be parallel to y, and the variation of stress will be along z. This is the difference. Okay. Now, in the first question, they asked first to determine the maximum stress. So this is a simple question here. The cross section is very simple. It's a rectangle. And we know that for a rectangle, we have that the inertia, if you are dealing with the first scenario, the neutral axis should pass by the centroid and should be along z, which is the direction of the couple moment vector. So inertia about z, izz axis is equal to this dimension, which is, let's say, b1, and this is h1. Okay, so we should do b1 times h1 cube over 12. b1 here is equal to 12 millimeter. h1 is 20. So the inertia about the axis is 12 times 20 cube over 12. Now here, of course, no need for a parallel axis theorem because already the centroid we just have a rectangle, so the neutral axis will pass by the centroid of this rectangle. Now, in order to find what is the maximum stress, okay, knowing the value of the moment, we can use the formula that sigma maximum is equal to the bending moment times the farthest distance from the axis over the inertia. And here, because you have a rectangular cross section, so C1 and C2 are equal. Okay, so C will be just equal to H1 over 2, the height over 2. So it's 20 over 2, which is 10. Okay, so here C is 10. So if you want the absolute value of your maximum tension and maximum compression will be equal because you have same Y top and Y bottom are equal. Okay, so and in general, if you have different C's, if they just ask the maximum stress, they don't specify if it's tension or compression, you take the largest distance. Between C1 and C2. But if they specify what is the maximum tension or what is the maximum compression, then you should look which side is subjected to tension. Let's say you have a moment like this. Which side is subjected to tension? This one. So I just choose this the C from neutral axis to this level. Okay. So be aware of the questions I ask you for. Now, so this formula will give you the maximum stress, which is by just replacing the bending moment, C, which is H over 2, and I is the inertia about your neutral axis, which you already calculated. So we get the maximum stress within our section. Now, we have developed together in the course material a relation between the radius of curvature and the bending moment. So you can just say to find the radius of curvature, I just have to use 1 over rho equal to the bending moment over the modulus of elasticity, which is given here in this problem times I. Now pay attention for units. To get rho in meter, use M in Newton meter, use E in Pascal. Here they provided you the modulus of elasticity in gigapascal. So all you have to do is to convert from gigapascal to Pascal. So 200 gigapascal is 200 times 10 to the power 9 Pascal. And you have the inertia is equal to the calculated value, use it in meter form. Okay, then you will obtain the value of rho in meter. Okay, so this is how you can solve for the maximum stress and for the radius of curvature. Now, what will happen in the other scenario? Just the direction of the neutral axis will change, and also you will have a radius of curvature in the other direction. Because look, whenever you apply a bending moment where the moment vector is along Z, then your radius of curvature will be along Y and the variation of stress will be along Y, while your neutral axis will be along Z. Now, when you reverse the scenario, if you solve the same problem now, assuming that the couple is about Y-axis, then you are applying a couple about Y. Okay, when you apply the couple about Y, this means that, look, you will do this. So here you will compress this part, and if the moment is along positive Y, okay, you will compress this part, and this part will be in tension. And then due to this bending effect, okay, you will have the center of your curvature will be up, will be along Z like this. So you will have a bending in this way, like this now. This is your bend, okay? And you can determine your center of curvature. Then in this case, your neutral axis will be along Y direction, okay? So your neutral axis will be along Y, and you will have that the radius of curvature will be measured along Z direction, okay? So in this case, we say that for my section, the neutral axis will be along the moment vector direction. So this is my new neutral axis. And then I want to compute the inertia about this axis. So when I calculate the inertia, I will say that the inertia about this axis, Iyy, is equal to, now I will take the distance parallel to y as my b. So this is my b2 if you want, and this is my h2. So I just reverse if you want my dimensions. So I do b2 times h2 cube over 12. Or if I want to use the previous notation of b1 h1, then it will be equal to h1 times b1 cube over 12. Okay, so this will give me my inertia about y-axis, and then I should apply the exactly same formulas, but with updated value of I, and of course updated value of C, because now C is this height over 2, C is h2 over 2 or b1 over 2, okay, which is equal to 12 over 2 equals to 6 millimeters, equals to 6 millimeters. Okay, so now just I have to do the following replacement. I calculate I again, okay, I calculate C again, and then I replace into my equations sigma equal mc over I to get what will be the maximum stress, and I replace into the equation of radius of curvature to get my value. And then, as I told you, the radius of curvature will be along another direction. Okay, so we'll continue to solve more problems next time.